Okay, hello Discrete Math. We learned about set theory in the last 15-20 minutes of class on the second day of school, the Friday of the first week. And then this weekend I assigned homework. Let's go over it. These are just a whole bunch of little stupid annoying problems that essentially just get you comfortable with the notation of set theory if you're not already comfortable with it. So hopefully it didn't take too long. And some people will learn something. Let's go over it. All right, I started to write the very first problem up on the board, and the very first problem said, consider the universal set. Okay, this is a concept that is kind of a little silly. I don't maybe want to talk about, but yeah, you know, let the domain of discourse, so to speak, the set of all possible numbers, possible objects that we're going to consider, be A, B, C, D, E, 1, 2, 3, 4, 5. This is just, this very first problem is just testing, do you just understand, the most basic vocabulary of set theory? I think we do. I accidentally assigned problem C, which is just a stupid problem, because set A is given to you as BCE 421, and set B is given to you as CEB 124. I think I've been assigning this problem for 8 years, and only now am I realizing that these are just the same set, and so this is just a silly question. They have now 12 questions they want to ask you about this pair of sets. The first question is D an element of A? No, D is not an element of A. Okay, 1 down, 11 to go. Is A a subset of B? Yes, A is a subset of B. I write it like this, but our textbook and many authors write it like that. Next question. So that's a yes. Is B a subset of A? Yes. Is A equal to B? Yes. And in fact, two sets are equal if and only if they are each subsets of each other. So one often way to show that two sets are equal is to you first show, you show that they're subsets of each other. Okay, next, are A and B disjoint? No, they are not disjoint. In fact, they are completely overlapping. What is the size of A? The size of A is 6 because there are 6 elements. What is the size of B? The size of B is also 6 because there are 6 elements. What is the complement of A? Okay, the complement of A is all the things that are not in A relative to the universal set. So that would be, in this case, A, D, 3, 5. So that was pretty chill. And now they're probably going to ask me for, no, good. A union B, okay, well, A union B in this case is just, I don't feel like writing it out, it's just A. What's A intersect B? It's also, A intersect B is also just A because it's the same set. A minus B would be the empty set because, everything that's in A that's not in B, well, that's nothing since they're just the same set. And B minus A is also the empty set. Okay, so sorry about picking kind of the silliest one. Good, one problem down, like a bajillion to go. 4C asks you to write some things in set builder notation. So let's do that. What is the set? They're giving you the set -3, 9, comma, -2, 4. These are ordered pairs. -1, 1. Okay, I think it's already clear what's going on here. These are the set of ordered pairs such that the right one is the left one squared. And there are some dots which are supposed to indicate that the pattern continues or whatever. This is frankly just like a middle school problem. Can you write this out in set builder notation? Yeah, I can. It's the set of all ordered pairs of the form x comma x squared such that x is an integer. That seems like the smoothest way to write it with the fewest number of variables. Good. Woo! Moving right through this. 5C says, convert the following into set builder notation. Oh man, I gave you another one of these. I thought I considered not doing that, but too late. 125, -64, -27, -16. No, I take it back. I wasn't paying attention. 125, 64, 27, of course not negative 16, negative 8. And then negative 1, 0, 1, 8. Okay, and then dot, dot, dot. Okay, one cannot help but notice that these are all the perfect cubes. And so what is this? It's the set of all things of the form x cubed, such that x is an integer. So yeah, just kind of practice with this kind of thing. Did I just do the wrong problem? I did. That was 5a, which I did consider not assigning. And in fact, I did not assign it. So what I did assign was 5c. And 5c, sorry about that, is 0, 1, 1681, 256. Okay, so this is a finite set, so you might as well just leave it as is, but if you want to write it in set builder notation, you can. What do all these numbers have in common, maybe? They're all perfect fourths. So this is all the numbers of the form x to the fourth, such that x is an integer and x is between 0 and 4 to the fourth is 256. There we go. Okay, boom, boom. Yeah, let's just erase this board and keep going. Dead time, dead time. Oh man, gonna have to do some emergency board cleaning. Okay, more sort of easy, tedious problems. 6a says, construct a properly labeled Venn diagram for each of the following triplets of subsets from the universal set. So again, this universal set concept. So this makes sense, maybe, you know, if you think of A through G as being the 7 members of a class or something like that, then that's like the domain, and so it does make sense to talk about that. Okay, let's see. And then we have set A, which is A, B, C. We have set B, which is B, C, E, F, and we have set B, C, F, G, and we have set C, which is B, E, F. All the work is like reading and writing. There's barely anything to do. Shade in the region A intersects B minus C. Okay, this is again just a middle school problem, right? What are we gonna do? Oh man, this is kind of a waste of time. Normally I would go over this homework by putting it all on the board, everyone simultaneously, and then we would spend sort of 10 minutes just kind of like pointing at each problem for 1 second, but okay, too bad. Here we are. Let's go. I guess I gotta like do this, right? So let this be A, let this be B, and let this be C, and using a different color, what are all the things? Well, what's in A? A, B, and C. Actually, B is in all of these. What am I supposed to be doing? Construct a properly labeled Venn diagram for each of the following triplets of subsets, place yourself in the proper region. Okay, so yeah, this is, oh man. Alright, well, I guess we just gotta go. So let's take A. Where's A? It's only in set A, so I put it there. Boom. Let's take B, we did it already. C, where's C? It's in A and B, but not C. So C goes here. Where's D? It's nowhere, so it's out here. E is only in here. F is in both B and C. Thought that was another one of those. If I do this wrong, it's really embarrassing. And then G is just in B. E is, well, I guess I could like count or something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total things. So that should be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I probably did that correctly. And is that everything? A, B, C, D, E, F, G. Wonderful. Okay, now we get to do the problem. Construct a problem. Okay, now what are we supposed to be doing? Shade in the region A intersect B. B minus C. All right, I think I can do that. A intersect B, parentheses, minus C. So that's everything that's in A and B, but not in C. Yeah, so it's just this. Cha, 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 cha. And in fact, this is just going to be a set containing just the letter little c. And then we are supposed to do something else. List that set, check, and list the set A union B intersect C. Alright, I think we can do that one as well. Let me get a green for that or something. What am I supposed to do? I'm supposed to take B intersect C, so that's this, and union that together with A. So that's going to be all of this business, and therefore this is the set A, B, C, F. Great. Good. Another one down. 7. Construct a properly labeled Venn diagram for each of the following triplets of subsets from U equals. Is this just kind of like the same problem, basically? I think this is just like the same problem. I considered not assigning this also, but then it looked like there was something fascinating going on, perhaps. But also, perhaps that could have been wrong. So I'm sorry if I wasted your time. Let U be W, X, Y, Z, and 1, 2, 3, 4. 1, 2, 3, 4. Oh yeah, high quality video. Please. Okay, so I have a set A, a set B, and a set C. It's occurring to me as I'm doing this that there might be like a better way to go over homework. W, X, Y, Z. B is 1, 2, 3, 4, Z. 1, 2, 3, 4, Z. C is WX1 and WXYZ. 1, 2, 3, 4, Z. WX1. I think we're ready to go. Construct a properly labeled Venn diagram each of the following triples, then complete the additional parts of the problem. Okay, so yeah, it really is like I'm supposed to really be doing the same thing again. So let's do it. No point in stopping now. So this is set A, this is set B, this is set C. Where does everything go? Well, W and X are in both A and C. So that's W and X. So cha 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 cha. Y is in just A, but Z is in both A and B. So boom boom. And then 1 is in both B and C. Cha 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 cha. But 2, 3, and 4 are in just B. So yeah, I guess I can just do something like that. 2, 3, 4. Okay, great. Now what am I supposed to do? Well, what should be the proper value, this problem then asks, of A, of B minus C minus A? Alright, so I don't even know how to answer this question. B minus C minus A. So I suppose what's going on here is the problem is that this is not associative. Step difference is not associative as subtraction is not associative. And so, if you sort of do this wrong, you know, it'll be wrong. And to me, then, I think it's probably a bad idea with an uncommon non-associative operation, such as set difference, to leave off the parentheses. So if I saw this, I would probably ask for clarification if I was writing a problem where this is the answer, I would add the parentheses. But I suppose that there is some kind of convention of going from left to right. Gossett's telling me to be careful, but I don't really know, that doesn't really help. So I choose to interpret it this way, and I guess this problem is in the back of the book. So I'll just do this and then I'll go see what happens. So Yeah, what is it? Well, if that was the intended answer, then I look at all the things that are in B but not C, so that's 2, 3, 4, Z, and then I also take out the things that are in A, so I guess this is just the set 2, 3, 4. Unless there's some convention that I'm supposed to right associate that I'm just not aware of. So, yeah. I take it back that this is a good problem. It's just not really. So, good. A, what is A? Okay, A intersect B complement, and A intersect B union C. A intersect B union C. Okay, this stuff I can do. This is still just middle school. A intersect B is everything that's in A and B, so that's a lot of stuff. It's almost everything. It's W, X, Y, Z, and it's 1, 2, 3, 4. In fact, it is everything. And so, try again. A intersect B is just Z. So the complement of that is everything except for Z. So it's W, X, Y, 1, 2, 3, 4. And finally, this last problem, A intersect B union C, it's just going to be Z plus everything that's in C. So that's going to be W, X, Z, and 1. Alright, I take it back. This was not an exciting problem. Let me pause this video for a second and be right back. Okay, we're back. By the way, I looked up what Gossett had to say in the back of the book regarding his set B minus C minus A, for which he told us to, quote, be careful, unquote. And the answer in the back of the book says, haha, got you. Set difference is not associative, so this is just an ill-formed expression. So actually, Gossett wanted you to just refuse to do the problem at all. Okay, and that's pretty funny. Alright, that's all I have to say about that. Let's keep going. 9E. Maybe these get a little bit more fun, but maybe they don't. 9E. Find the symmetric difference. Aha! Here's a new thing that didn't get mentioned in class because I didn't feel like it, because ultimately it's not really important, maybe. The symmetric difference between two sets is defined to be A minus B union B minus A. Alright, so what's up with that? It's everything, if this is A and this is B, then it's everything that is in A but not B, and everything that is in B but not A, so it's like all this. So it's essentially like XOR. If I wanted to give an alternative definition of the symmetric difference of two sets, not in terms of union and set difference, as was done in the book. Here, union, by the way, I think it's worth mentioning. Okay, in this class we, in this class we did exactly what the book does, which is introduce set theory first, and then talk about logic, although maybe that's backwards. Because, of course, when we defined A union B, here's some interesting content happening right now. How did we define A union B? Well, I probably just said something like, it's the set of all x such that x is in A or x is in B. And here I just expected everyone to know what I meant by or, but of course if something is in A and B, then it does belong in the union. So the only way to interpret this or correctly in the definition that I gave in class, and okay, this is still just middle school stuff, but the only way to interpret that or is inclusively. In other words, we should have interpreted it inclusively. So, had we done propositional logic first before set theory, then I may have written at this moment like, or using the symbol, which makes it totally unambiguous that inclusive or is intended. So what is, now that we have done propositional logic, it's possible to give a definition of the symmetric difference in an analogous one as the set of all x such that x is in A, like, XOR x is in B. or you can use the symbol that's maybe less common or something. So that's really what this is. Okay, do we care about this? Not really so much. So what do we have? We have some set A, which is 1, 4, 5. And we have some set B, which is 1, 2, 3, 5. And so, what are we doing with these two sets? We're taking their symmetric difference. So we need all the things that are in one set but not both. So that is going to be just like 2, 3, 4. So that's all that's going on there. Okay, cool. More. 13, A through D. These must have been like important or something. Form the power set. Okay. This I have found in the past is something, well, I don't think this is necessarily so important, but it is something that people struggle with, actually. So oftentimes I find in class that people got this wrong. So, okay, what is the power set of the empty set? Well, that's a very strange question. So what is the power set of the empty set? Well, what is the power set in general? It's the set of all possible subsets. So let me make sure I do this correctly. The power set is going to be the set of all possible subsets. Does the empty set have any subsets? Yes, the empty set is a subset of the empty set. Therefore, the answer to the power set of the empty set is it's the set containing the empty set, which is different from the empty set. The empty set is a set with no elements. If you want to give a definition of the empty set, it's like this. It's a set with no elements. However, this set, the set is a set that does have one element. Its one element is the empty set. And in fact, I can even write something like this empty set, a set, is an element of the set containing the empty set. So, yeah. And so just kind of trying to clarify here, you know, the size of this is in fact 1. And that's actually kind of interesting because we know that the size of the power set of any set is 2 to the size of that set. And so we would actually predict that because 2 to the 0 is 1, that the size of the power set of the empty set would be 1, which it is. Okay, woo woo, having some fun. What now? How about a set with just a single element? So now the power set of a set with just a single element, which is alpha. Okay, what's the power set again? It's the set of all possible subsets. So what are the possible subsets of this set? Well, one subset is just the empty set. The empty set is a subset of every set. And then the other one is just the set itself. And okay, it bears maybe repeating here. What is the definition of subset? So this conversation is actually a little bit useful. What's the one we're doing right now? What does it mean for A to be a subset of B? Here, if you really want, I can put that little thingy there, but I mean, you know, it doesn't matter. I'm just saying it out loud. Subset. A is a subset of B if and only if. Okay, the definition you get in middle school is if every element of A is an element of B. Okay, and that's just exactly correct. But we may explain that definition more carefully and more unambiguously using predicate logic and quantifiers. So the sort of big boy, big girl definition of A is a subset of B says that for all x, if x is an element of A, then x is an element of B. This is basically a direct translation of every element of A is an element of B. For every x, if it's in A, then it's also in B. Okay, great. Why are we talking about this right now? Because it clarifies why the empty set is a subset of every set. Because given any generic set whatsoever, then you know, you can just convince yourself of this by simply observing that every element of the empty set is an element of A, and there are no elements of the empty set. So if you find that convincing, okay, great. But if you don't find that convincing, you could peek down one level of detail into the definition of the subset relation and see that what this is really saying is that for all x, if X is in the empty set, then X is in A. And now you can ask yourself about this conditional, and what you can see is that because the empty set has no elements, then this statement, X is an element of the empty set, is just guaranteed to be false. And so what we see here is an example of our mathematical definition of conditional, the propositional logic definition of conditional, sort of doing some kind of work for us in a certain way. And so this sentence we say is vacuously true. This sentence, if X is an element of the empty set, then X is an element of A. It's vacuously true, the conditional is true, because the antecedent is false. So it's sort of a stupid conditional. But this is another example of why it's actually quite reasonable to fix our interpretation of conditionals so that they return true when the antecedent is false. That's explaining why the empty set is a subset of every set, and of course also, that's good enough for me. Okay, good. More, what else? Now they're just going to make me do this like 2 more times, right? So for C, they're asking for the power set of a set with 2 elements, and for D, they're asking for the power set of a set with 3 elements, alpha, beta, gamma. Okay, so we can just kind of like, do this really fast. Here there are 2 elements, so for each of those elements, they can either be in the subset or not, and so we expect 4 subsets, and there just are 4 subsets, right? The empty set, a subset of every set, the singleton set, alpha, the singleton set, beta, and then just the set itself is also a subset. So that is the power set, the set of all possible subsets. And finally here, we should expect 8 of these, and indeed that's exactly what we get. The empty set, the set containing A, the set containing B, the set containing, or beta, the set containing gamma, the set containing just alpha and beta, the set containing alpha and gamma, the set containing beta and gamma, and the set containing alpha, beta, and gamma. Chop, cha-cha. Alright. Oh man, this is just taking forever. But I want to be done now. Oh, okay, this next one is totally awesome. So, let's go. This is the most fun problem on this section of the homework. Maybe it's the only fun problem on this section of the homework. Okay, so let's go. 16 says, design a Venn diagram that shows the most general relationship among 4 sets. Hint, use ellipses instead of circles, including the blah, 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 blah. Okay, good. So what's going on here? Dude, make a Venn diagram. All right, done. So the kind of Venn diagrams you see in elementary school look like this, where this is A and this is B, and it's beautiful. I love it. Then, in advanced elementary school, otherwise known as 6th grade, you add in a 3rd set, C, and now, what do we have? We have sort of all regions represented if you have these 3 sets such that there's kind of some overlap between them, sort of in every possible combination. Then you need sort of 8 regions depicted, and these are the 8 regions. So everything's looking good. But if you try to add a 4th one, things get really complicated. Let's actually just try to do it. So here's a circle A, here's another circle, here is another one. Okay, and so what is this? This is A, this is B, this is C. Okay, so now suppose I try to draw in D. Where is D going to go? Alright, well, you might be thinking initially like, okay, let me just kind of get up here and sort of try to cut through. You kind of need to cut through every region, right? Because you want your 4th circle to exist in such a way that it sort of divides every one of these 8 regions in half. but there's a kind of a geometry of circles which makes this impossible. I haven't really thought through the exact proof of why this is so, but if you kind of try to do, say, that or something, I don't know, that seems to have done a good job, right? I've divided after all this space, the space outside, in half. Great. I've divided this space in half. That's looking good. I cut, but like you kind of, I think you already see sort of somehow like it doesn't work, right? Because down here, the things that were in just C but not A and not B, now we have no sort of region associated with the things that were in C and D are not represented here. And also, I think this region are the things that are in A and B but not C. Now they're all inside this circle, and so we sort of like fail or something, right? I can't make this purple circle any bigger. If it's big enough so that it cuts through the C region, then it will enclose all of this region. And so I'm very sad. Actually, if you count all the dots, you will have less than 16. There should be 16, but there aren't 16. There's going to be like 12 or something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And they're really only missing by 1? I think not. I think actually what I have is possibly something even worse, which is, give me a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15, but I think 15 somehow overstates how good of a job I did. Oh no, because I did the red dots right. So 14. So yeah, that seems to be actually about right. 14 is decent, but yeah, it's this one. The two sad faces are here and here, because I have no region associated with things that are in A, B, but not C, and also not D. Is just not depicted here at all. And the other thing not depicted are things that are in C and D, but not A and B. Okay, so somehow I just like can't do this with circles, although I would be interested in a more low-level proof of that, using the kind of geometry of circles that this can't be done. I haven't thought about this that much. So what are we supposed to do? We're supposed to, this you might think, you just can't do this. Actually, if you Google like, Venn diagram 4 circles, you will find tons and tons of pictures on the internet of 4 circles intersecting in a Venn diagram, and they just don't have all of the possible regions depicted. So that's kind of just terrible. All right, what can you do? Well, you can do it with ellipses. Haha. This I find really hard. But I did practice just before this video. So let's go. Let's see if I can do this. Although I'm not sure I can give an explanation of sort of how I came up with this, because in fact I didn't come up with it. So I sort of have one ellipse, let's call this A, and then I have like another ellipse, call it kind of B, and they're sort of off at an angle. And now I want to make like another one or something. Hope I'm doing this right. And I want this other one to kind of come in sort of like this. And I guess I need, I guess I need it to go, yeah, that's right. I want it to go kind of jump like this. Yeah. And now, let's see, have I already done a good job? I think I've already done a good job, because I should have currently 8 regions. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And so I've sort of set things up well, right? Because now I had kind of A and B as my first pair of ellipses, so they're in the normal orientation. But now this third ellipse, C, has sort of cut through ellipse A, and it cut through all 3 of the regions, 1, 2, 3, and I guess the outside in such a way. Okay. I'll just now finish it off. Now I sort of need my 4th ellipse, D, to cut every one of these regions in half. And so I think what I now want to do is kind of come in, cut this in half, cut this in half, cut this in half. So I've cut 3 in half so far. Now I'm going to cut 4 in half, 5 in half, 6 in half, 7 in half, and by closing that up, 8 in half. Actually, that's a pretty good explanation of sort of why ellipses will do the job, because with ellipses, unlike circles, you can sort of make them bigger and sort of stretch them into regions without accidentally sort of enveloping other regions that you wanted to not envelop. And so if I've done this correctly, and I think I have, I should have 16 separate regions representing the sort of 16 possible binary, I don't even know what to call it, the 16, given arbitrary sets A, B, C, and D, then there are 16 possible sort of regions of overlap or something. There's probably a better term for that. Well, anyway, let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That is just beautiful. I love it. Okay, while looking this up on the internet, I found like another one that's kind of sort of beautiful as well. Let me show it to you. Here is, here you can do it with rectangles. So you can say, okay, take this rectangle A, and now let's take another rectangle B. Is this what I want to do? Yeah. Another rectangle B. Okay, great. So this is now B. Okay, and now I want a rectangle C that cuts through all these regions. So let me do that now. Let me switch to a new color. In fact, what I might do is sort of just very lightly go through. That's A and B. Okay, and now I want a new rectangle. So this new rectangle is going to cut through all three of these. So I'm going to stick it here. And so this is, I think, kind of brilliant. So this is C. Perhaps on the outside is a better spot for these letters. So that's C, and that's B. And now, what is this? This C rectangle? I'll sort of do in. Well, I guess I'll do it in blue. And finally, I need one more rectangle to intersect every one of these. So I currently have 1, 2, 3, 4, 5, 6, 7, 8 regions. And I guess I'll just do black now. So now I'm going to cut through all 8 of those regions. 1, 2, 3, 4, 5, 6, 7, 8. With like a rectangle that's just chilling here. Cha. Cha, cha. And this will be D, and this will be, I guess, purple. So, shump, 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 like that. Okay, so if you want to kind of make some sense of what's going on here, now I'll say, okay, sort of big green dot in all the regions that are supposed to be in A. So, oh yeah, this is just beautiful. And 1, 2, 3, 4, 5, 6, 7, 8 regions. So half the regions should have an A in them, of course. And then half the regions should have should be. For some reason I can't say what I'm trying to say correctly, but. And then what regions are representing C? So C, 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 C. And finally, the regions representing D are going to be here, 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 and here. Okay, and so sure enough, 1, 2, 3, 4, 5, 6, 7, we have 16 regions, and we have, you know, things that are in just A, things that are in just B, things that are in just C, things that are in just D, things that are in, you know, A, just A and C, just A and B, just A and C, and et cetera, et cetera. So I think that's quite cool. Okay, that's 16. I think I gotta like finish this up later, I guess. No, let's just do this right now. I'm just gonna call out the rest of these really fast. So 17. Determine whether it is always true or else false in some cases. Give some justification for your answer. Actually, let's just not go over 17 and 18. I just don't feel like it or something. Let's just go straight to 22 and then wrap up the video. So 22. I asked you to do A, C, D, and E. What's A? A says, which of the following collections of subsets form a partition of the integers? The set of positive integers and the set of negative integers. So, Z plus and Z minus. Is that a partition? What is a partition? It's a collection. The partition of a larger set is a collection of non-empty sets which are non-overlapping, so they are pairwise disjoint, and they exhaust the set, so their union is the set. So is this a partition? Answer, no. It is true that these two sets are disjoint, so that their intersection is empty, so that's good. However, it's not true that Z plus union Z minus is the set of all integers, because you forgot about 0. So therefore, that's not a partition. Okay, part C. The set of integers evenly divisible by 3, the set of integers leaving a remainder of 1 when divisible by 3, and the set of integers leaving a remainder of 2 when divisible by 3. Well, that's just the Euclidean division algorithm right there, right? The Euclidean division algorithm says that any number, A, can be expressed as some number of 3's plus some kind of remainder, where that remainder is guaranteed to be less than 3, and that this can be done uniquely. Therefore, every number will either leave remainder 0, remainder 1, or remainder 2 when divided by 3. Therefore, it is true, so I'll just write yes, that that is a partition of the integers. In fact, I think this is even the example I gave in class of a partition. It's the set of all numbers which leave a remainder. The set of all numbers which are divisible by 3, so I'll just do that. The set of all numbers which leave a remainder 1, and the set of all the numbers that leave a remainder 2. These sets are pairwise disjoint. The intersection of any two of them will be empty, but also when you union them all together, you get all of the positive integers. I guess we're including negative integers too here, so that's fine because our Euclidean division algorithm, does that. So I should go like dot 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 and dot dot dot, and what is that, like -2 and -1. Okay, so boom 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 boom. Did I not do 21C? I now realize. Okay, I'll go back and do 21 in a second. Oh man. 22, that was 22A and 22C. What's 22D? 22D says the set of integers not evenly divisible by 2. Okay, so let's just call those, odd integers. And the set of even integers, okay, so evens, and the set of integers leaving a remainder of 3 when divided by 6. Oh man, the set of all integers leaving a remainder of 3 when divided by 6. So that's all the numbers of the form 6n plus 3, where n is an integer. Okay, well, what can we say about these 3 sets? Well, it is true that if you union them all together, you get all the integers. So it's exhaustive. However, it is clearly not a partition because the sets are not pairwise disjoint. For example, if you take the odds and you intersect them with the set of all numbers leaving a remainder of 3 when divided by 6, you get that there are some things in this set, such as 3, 9, etc. So therefore, it's not a partition. Okay, and 22e, the set of odd integers and the set of integers divisible by 4. This is actually a great homework problem. Set of odd integers. Okay, so now we have the odds and the set of integers divisible by 4. So this is the set of all the numbers of the form 4n, where n is an integer. Is this a partition of the integers? Well, the answer is no, because now we have kind of like 22a, I guess. It is true that the odds intersect all the numbers of the form 4n is empty, so there's no overlap, but it's not a partition because it's not exhaustive. So it's just not true that the odds union the set of all numbers of the form 4n is the set of all integers. That fails, and that's why the answer is no. For example, you are missing the numbers which are even but not multiples of 4, like 6. Okay, finally, because I skipped it, 21c. What is 21c? It says, consider the set S, which is A, B, C, D. And the question is, list all possible partitions of S. So that's kind of exciting. What are the ways to do this? They have to be non-empty, right? So here are my options, I guess. I can do A and then B, C, D. That's one possibility. I can do B and, wait, I think there's going to be a lot of these. And A, C, D. I can do C and A, B, D. I can do D and A, B, C. Okay, more. I can, okay, so this I think it counts now for all the partitions of the set A, B, C, D into sets of size 1 and 3. So actually the only thing left are the partitions of A, B, C, D into sets of size 2. And I guess there's just going to be 6 of these, right? So, because of math. And what are they going to look like? Yeah, I can put A and B together, or no, maybe even less than this. Maybe just 3. Hold on, now I'm confusing myself. I think maybe there's just 3 of these, because if I put A and B here, then C and D will be here. If I put A and C here, then of course B and D will be here. If I put A and D here, then I expect BC. But now I think I'm just done. I hope I'm not messing this up, but I think I'm just done now because there are no other possibilities, right? Because if you think, okay, now let me choose, A, B is already done. So we already have sort of a pairing of every number with every other number. One way to think of this is that A's got to go somewhere, and then there are just 3 choices of who gets put with A. And once you choose one, once we're in the, oh, no, what am I talking about? These are just the partitions into 2. Okay, wait, so there are a couple more. Good, that was almost a mistake. So I haven't done anything wrong yet, but I'm definitely not done. Because then there are the partitions in which we divide it up like more, right? So like A, B, and then like C, D. Yikes. And then there is like A, C, B, D. And now, okay, I guess there's only 3 of these? Probably should have thought about this problem first. And then A, D, B, C. So that's all the ones in which A, C, A, B, and A, D are alike. But yeah, this is like a 4, so there are actually going to be 6 like this. So 3 more. Squeezing this in. So there are going to be, 3 more like this. And then, what are they? B, C, A, D, B, D, A, C, and finally C, D, A, B. And then there's the one in which they're all alone. So A, B, C, D. Alright, so I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I believe the answer is that there are 14 partitions of this set A, B, C, D. But my level of confidence in that is somewhat low. Let me just check in the back of the book real fast and then we'll end this video. I'm not even sure this was one of the problems that is in the back of the book. Nope, it's not. Alright, so I think that's right, but I easily could have made a mistake. Anyway, goodbye. Video over. Okay, back for a 5-minute power round. Here are the problems we skipped. These are the true-false questions. They're actually like pretty hard, tricky little problems, and God wants you to give a whole like explanation and stuff like that. That seems too much for me. So for all the true-false problems in this book, whenever they come up, I just want you to think deeply about it and just give your answer, but skip the justifications, which I mentioned. So I won't give the justifications either. I'll just say them out loud. Let's go. This is just a test of your understanding of the notation. Some of these are obvious. Some of them are more complicated. If A is a subset of B, then A is not equal to B. This is false. What do they say? They say it's just always true or else false in some cases, otherwise known as false. So this is false in general because we say, well, basically because every set is a subset of itself. And so when we say A is a subset of B, we include the possibility that A is equal to B. So certainly I cannot conclude that A and B are different. If A is not a subset of B, sort of then what? Okay, there was a rest of this sentence, but let's, instead of evaluating whether the rest of the sentence seems right, let's do the real thing, and let's write out on a very sort of low technical level the definition of what it means for A to be a subset of B and to negate it. In other words, as we said in an earlier part of this video, so remember learning happening now, we said that the meaning of the A is a subset of B is that for all x, if x is an element of A, then x is an element of B. Okay, so that's kind of the definition of what it means to be a subset. And so if A is not a subset of B, then I stick a not out front. And now I'm going to lean on my understanding of the various underlying logic to just kind of like simplify this statement. Okay, well we're going to do sort of 2 things at once because I don't have a lot of room. Let's distribute this negation through the universal, which changes this to a there exists, and then, yikes, which changes this to a there exists, and then there's like a not sitting out here. But before I distribute that not through, let's also rewrite this conditional, is because any conditional P, R, or Q is really like not P or Q. So this is really like says X is not an element of A, or X is an element of B. And now, finishing it off by distributing the negation through this disjunction gives me X is in A and X is not in B. So that's like kind of very satisfying. It tells me that, the in fact precise negation of the statement that A is a subset of B is the statement that there is an element which is in A and which is not in B, which is what the rest of this sentence was in part B. So this is therefore true. Okay, C, the empty set is an element of every set. That is a misunderstanding. No, the empty set is a subset of every set, but the empty set is not an element of every set. And some people are potentially, confused by this. So don't be. For example, the empty set is not an element of, I don't know, the set of integers, for example. The set of integers are a bunch of numbers. The empty set is not a number. don't say anything more about that. So, okay, good. So you just have to distinguish between element of and subset of. So that was one of the goals of this homework assignment, if you didn't already have this all clear. Part D, the size of the set containing the empty set is 1, but the size of the empty set is 0. Well, we went over this exact fact when it came up earlier. I must have been remembering sort of this problem. So yeah, you have to be sophisticated enough in your notation, and if you have a misunderstanding of the notation, then you could misread, other people's mathematical arguments. So I think it is important to kind of master reading comprehension of the notation. The empty set is a set with no elements, and so the size of the empty set is 0. This is just like true, and yet the set containing the empty set is a different object. It's a set with one element. That one element is the empty set. And so indeed this has size 1, as we said earlier, so this is true. E, the complement of A is just A. Yeah, that's just also true. Do I have anything deep to say about this? I don't think so. Kind of a silly problem. If you're not in A, then you're just in A. And the complement of the universal set is the empty set. Yeah, sure. Because what is the complement of U? It's just U minus U, and that's just the empty set. Okay, G, for all A and B, A minus B is B minus A. That is just absolutely false. If A is the set of all swimmers and B is the set of all flyers, then A minus B are all the things that swim but can't fly. But this would be the set of all things that can fly but can't swim. So those are just separate. And in fact, I guess those will always be different unless A and B are the same. I believe that unless A and B are the same set, A minus B will always be different from B minus A. So not only is it not true in general, but it's almost never true. H, if A and B are disjoint and C is a subset of A, then B and C are disjoint. Okay, well, we can make a picture of this H. So the picture is kind of something like this. Here's A, here's B. This is kind of like the middle school approach. And they're disjoint, so they don't overlap. C is a subset of A, then B and C are disjoint. So yeah, this is just absolutely true. Can we do something sort of more deep about this? We probably could, because do I want to do this though? Probably not. Yeah, I mean, take any x. Well, what does it require to show that B and C are disjoint? To show that B and C are disjoint, you have to show that B intersect C is the empty set. So is this true? Well, what is B intersect C? To show that it's the empty set, what I could do is I could take some x which is in B intersect C. Okay, what do I know then if it's in B intersect C? I know that x is in B, and I know that x is in C. Alright, well, I also know that C is a subset of A, so everything that's in C is also in A. So I also know that x is in B and x is in A, because everything that's in C is then also in A. But now I have an x which is in B and A, so that means x is in B intersect A, but A and B are disjoint, and I know that therefore, by the definition of disjoint, that B intersect A is empty, so now we just have a contradiction, right? X can't be in B intersect A because B intersect A is empty. Contradiction. So therefore my assumption that there was an x in B intersect C led to a contradiction, and so B intersect C must be empty. That was like a proof. We had some problems like this on the other homework as well. Okay, finally for I, this is just also false. These are ordered pairs. So, when the order's all wrong, the order's all wrong. So for example, well, I don't think I want to give an example. Okay, good, that was 17. 18. If A and B are sets, then A minus B is a subset of A. That just must be true, right? Everything, well, what is this even saying? This is saying, that the set of all things that are in A and that are not in B is a subset of A. Well, of course that's just true, right? Because I have to show that every element of this set is also an element of this set. Well, every element of this set has the property that it's in A. And so every element of this set, is in A. So that's just true there for that one. The power set of the empty set is the same as the power set of the set containing the empty set. This is false. That just goes back to that distinction between those two things again. The empty set has no complement. I suppose the empty set does have a complement. The complement of the empty set would just be the universal set. So it's all the things that are not in the empty set. Well, everything is not in the empty set, so it would be the universal set again. I'm barely going to use this concept of universal set, so okay. D is kind of interesting. If A and B have the same size, and that size is some kind of finite positive integer, so not 0, and A is a subset of B. Okay, here I need to be careful that I'm writing it down the exact way he does. In 18D, he does use his little thingy. Okay, I don't think it matters. But A is a subset of B, then A equals B. Yeah, this just must be true, right? Because if A is a subset of B, then every element of A is an element of B. Well, A has n elements, so if every one of those n elements is also in B, then, and B only has n elements, then B can't have any more elements that aren't in A. Therefore, the only way for this to be true is if they're equal. I thought that was pretty convincing. E. For any set, the empty set cross or times A equals the product of A and the empty set equal. This is just true, right? Because what is the empty set? I guess I kind of hurt my knee. What is this, for example? What is the meaning of the empty set times A? Well, it's the set of all ordered pairs x comma y such that x is in the empty set and y is in A. Well, just stop right there. There is nothing in the empty set. So there just is no x in the empty set. So there just are no ordered pairs of the form x comma y where x is in the empty set. Therefore, this is a set of ordered pairs, but it's a set of no ordered pairs. If it's a set of no ordered pairs, then it is in fact just the empty set. So that's kind of interesting. And you can sort of do some deep things with this, actually. Because you can think of the size of the empty set times A as sort of, well, never mind, let's move on. F. If A is a set, then A minus the complement of A is A. No, that is, I believe, just false. A minus the complement of A, well, that's going to be, right, oh, wait, maybe that's true. A minus the complement. So what is this? It's going to be the set of all things such that x is in A and x is not in the complement of A. But if you're not, so no, this is just true. Sorry, I was being kind of stupid there. It's a set of all things in A minus the things that aren't in A. But if you take out the things that aren't in A from A, you've in fact taken out nothing, so it's just A back again. So of course that's true. Sorry about that. Okay, last two, G. If A is a subset of B and B is a subset of C, then A is a subset of C. Okay, and here's where, I mean, this is very, very annoying. So I've copied down what Gossett wrote, character by character. He insists on using this symbol, which to his credit, is more standard nowadays for subset. But then he just whips out, you have to be really paying attention. The third symbol here is the symbol for proper subset for him. I will never really talk about proper subset. So here, this sentence is false because I can't necessarily conclude that A is a proper subset of C, because it's possible, of course, that A could equal C. If A and B and C are all the same, then that would be that. Finally, H is, I think, maybe the hardest one of all. Take some arbitrary set A, construct a new set B. What is B? It's A, comma, the set containing A. And now the question is A a subset of B? If you don't think about this too carefully, the answer is somehow, of course, yes. But let's think about this a little bit more. what is B? B is actually a set with just precisely 2 elements. And those 2 elements are both sets. The set A and the even more weird set containing A. So, for example, suppose A were like the set of integers, for example, just to make this a little bit more specific. Well, if A were the set of integers, then what's B? B would be the set containing precisely 2 things. The integers and a set with 1 element, that element being the integers. So that's just weird. So now, is A a subset of B? The answer in this case would be no. And therefore this is false. Because what does it mean for A to be a subset of B? It means that every element of A is an element of B. But that's just not true. 3, for example, is an element of A, but 3 is not an element of B, because 3 is not in B. The set of all the integers is in B, as well as this other weird set. So this is very, very tricky, I think. And I was going to say one more thing. Oh yeah, so what is true is that A is an element of B. Okay, that was your introduction to set theory. We've done now 17 and 18. I probably didn't make any mistakes. The video is probably like over an hour. Goodbye.